The RL time constant. Just like we did with the resistor capacitor relationship, we need to do the RL time constant and determine how can we calculate the amount of current is flowing through a circuit at a given period of time. Because the inductor's basic action is to develop a voltage that opposes a change in current, it follows that current cannot change instantaneously in an inductor. A certain time is required for the current to make a change from one value to another. The rate at which the current changes is determined by the RL time constant. So we can define that time constant as a fixed time interval that equals the ratio of the inductance to the resistance. So we can see that in the mathematical relationship. Tau, the time constant, is the inductance divided by the resistance. The inductance in Henry, the resistance in ohms. So the easiest way to understand this is start working some problems. A series RL circuit has a resistance of 1 k ohm and an inductance of 1 millihenry. Whenever you see problems like this that have K and M, notice that the math is going to be made easier for you because here we have 3, here we have -3 as our exponential values. So what is the time constant? So let's set up the ratio. Tau is equal to L over R, 1 millihenry divided by 1 k ohm, and you can see that applying the laws of algebra for quotients, the 10 to the third can be moved into the numerator by changing the sign on the exponent to -3, and it simply becomes 1 times 10 to the -6 when the exponents are added together, microsecond. 1 times 10 to the -6, or 1 microsecond. So now what we need to do is look at what happens in increasing and decreasing currents, charge times, discharge times. So the charge time, the increasing current, in a series RL circuit, the current will increase to approximately 63% of its full value in one time constant. And after that, it grows in steps. Okay, and we're going to learn those steps, and you're going to apply them. In fact, in your notebook, write them down because you'll be using them a lot during this lesson. One time constant interval after the voltage is applied is 63%. So if you had 1 amp, that would be what? 0.63 of that amp. This buildup of the current is analogous to the buildup of a capacitor voltage during the charging of an RC circuit. They both follow an exponential curve and reach the approximate percentages of the final current, and we'll see that in the table and the figure to follow. The change in current over 5 time constants, as we'll see in the figure 1320, when the current reaches its final value, or 5 time constants, it ceases to change. So we've gotten essentially to the maximum. At this time, the inductor acts like a short, except for the winding resistance to the current applied, the constant current. The final value then of the current then becomes I final divided by the source voltage, or is the source voltage divided by the resistance. 10 volts, if that's your source, 1 k ohm gives us 10 milliamps of current after 5 time constants. So again, in your notebook, write down this little chart: 1, 2, 3, 4, 5, 63%, 86%, 95%, 98%, and 99% after 5 time constants. If we look at it graphically, we can see the exponential curve from 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. 5 tau then is in essence 100%, or the applied current. This diagram shows you what happens at each of those increments, each of those milestones. I'm not going to go through it, but it's pretty easy to follow. You can see the current in the series portion giving you your time constant values. Let's work an example. Calculate the RL time constant for the figure, then determine the current and the time each constant interval measured from the instant that the switch is closed. So we've got a 12-volt source. We've got our switch going to the closed position, allowing current to flow. The current flows through the resistor, 1.2 k ohms, through the inductor, 10 millihenries. So to calculate first the RL time constant, L over R, 10 millihenries, 1.2 k ohms, we end up with one time constant, 8.33 microseconds. The current then at each time constant interval is a certain percentage of that. So I final is equal to V source divided by R, 12 volts divided by 1.2 k ohms gives us a full current of 10 milliamps. So then using the time constant percentages as follows, then at one time constant the current is equal to 0.63 times 10 milliamps, 0.63 milliamps, or 8.33 microseconds. If we go all the way to the end, 5 tau, the current is essentially at 100%, 0.99 times 10 milliamps, or 41.7 microseconds. Now the discharge, the other side, decreasing current. Current in an inductor decreases exponentially according to the approximate percentages in this table and what we'll see in the following exponential curve figure. The change in current over 5 time constant intervals was illustrated in 1323. When the current reaches its final value, or approximately 0 amps, it ceases to change. So go ahead and write this relationships down in your notebook. One time constant, 37%, all the way to 5 time constants, or essentially 0. Again, you can see the exponential curve here as the current is decreasing in a decreasing current through an inductor. Again, a simple illustration here that goes through each of those steps of the decreasing current in an inductor. You can go ahead and go through it to prove to yourself. You can see again they've put a current meter in series with R2 to show how to measure the decreasing current. Okay, when we come back, the next thing we're going to look at is the response to a square wave. We have an ideal square wave here, and we have what actually occurs with the roll off and the roll on during a charging cycle. So when we come back, we'll take a look at this relationship.